Hello, my name is Kunchen Du. This is the final presentation for cross system engineering. So my system is solar system, and we have the two figures here. It would be introduce my background for design the system. The first one is show that the fuel resources will be exhausted in next few decades, where the three main fuel resources is coal, gas, and oil. It would be run out. And also you can see another one. This chart showed the U.S. energy consumption is mainly come from the fuel resources. It would account to around 70%. It's a big account, so it is imperative to develop renewable energy. In California, solar PV systems are increasingly becoming the first choice for company and institution because it is hardly to see the raining day or cloudy day in California. There is enough sunlight during the whole years. Also, with the reduction of the fuel resources and the increase in electricity price, a lot a large number of the institution or company are trying to use the new energy sources. And you can see these figures. It shows the price of electricity in California is increased year by years. So for a big building, it's a big consumption. And also, you know, a economical system of electricity is essential for any big scale company because this means high cost. So next, let's do the after the introduction of the background. Next, we do the concept development. According to the simple analysis, the solar system is need-driven system. It's easy to know because the system is designed to commercial field, and there's no very new technology development, and it also can eliminate the shortage of the normal system. According to the basic requirement of the new system, it should be economical and durable because this is the power system should be work for a long time, so it must be durable. So and it must have the rigid and maintainable, and also the power system must be efficient. It must have a good performance, and it have a good interface with another subsistence, and the system must be smart and safe. So this is the objective for my system design. And the objectives can be translated to the functional subsistence. You can easy to see the first subsistence is collected subsistence. It combined with the solar PV panels. It can collect the solar energy from the sunlight. And another one is storage subsystem. It's designed by the high volume battery bank because maybe the solar panel will collect the actual energy from the sunlight. It would be stored here. And we have the protection subsystem and the control subsystem. The protection subsystem can ensure the safe of the new systems. The picture is the battery management system is a portion for the protection subsystem. It can help engineers or users to monitor the situation of the battery. And the FPGA board is the controller can be coded to control the system. This is the control subsystem. And also we have the most important subsystem is power conversion system. Because the power comes from the sunlight, it's the solar energy. When it translates to be electricity, we have to make it can be used to the building load. We have to make the current and voltage to a special value like 1 and 10 volt and have a special direction. So the converter and the inverter is important. For the DC bidirectional buck boost converter is designed to change the direction of the current flow and also can buck or boost the voltage of the electricity. And the inverter is designed to change DC current to AC current. So this portion is very important. Also, let's introduce the initial architecture. And you can see the picture I created is the architecture of the system. We have a sun and we have a PV panels to collect the energy. And according to the transducers, the situation of the PV panels can be measured by the transducer, and the data goes to controller. And also the building load, the situation of the building load will can be tested by the transducer. The data goes to the controller, and also the data of the battery bank can be measured by the BMS, and the data will goes to controller. And the controller like a super brain, and they will give the instruction to the converter, and maybe it can change the direction of the energy. The electricity comes from the PV panels, maybe can goes to the battery, goes to the building load. The old instruction comes from the controller. Next, let's do the risk analysis. Because this is a big power system, so it means dangerous. Because the environment is high voltage, maybe high voltage could threat the health of the people. So this one is a main risk. And another one is the test. Because the dangers of the environment, so the test should be complex. We have to do a lot of preparation for the test. So this is risks. And also another risk is accident of weather. In California, there is occasionally earthquake and rainstorm. Maybe this risk must be a factor considered by the engineer in process of the development. After concept development, let's do the engineering design. First, according to the above risk and requirements, we have to do the prototyping of the systems. Like the first this one you can easy to know. This is the prototyping of the storage subsystem. You can see the virtual block of the battery. So we have the 72 functional cells connected in series, and each cell, as mentioned before, has 3.3 volt capability, and the total amount may be around 240 volt. And you can see the connection, the battery connection here. You can easy to see they connected in series, and we have the negative end, we have the positive end. And for this prototype is the connection of the BMS. BMS is the BMS can protect and monitor each battery cell, and using the BMS software, the user can control the different parameters like current and voltage within the software, and upload upload the profile to the BMS based on user settings. And this prototype is a user interface panel, so we can easily to see the user interface panel is very straightforward, and it can keeping track of the solar panel. We have the solar panel indicator, we have the building load indicator, we have the battery indicators, and the indicators can get data from the system, and we can monitor the health of them. And also we have the 3 light. If system is good, it's work normally, the green light will be open, and their warning or their fault happened, the information would be showed in the list, and the different light will be open, and to tell the users what happened. Also, we have the emergency stop button, which can safely shut down the system in emergency. And for this one, this is the circuit of the converter. Because we have the special parameter for the building load, we have the special energy need. Maybe in market we cannot find the perfect converter. So for converter we have to design by ourselves. So the DC-DC bidirectional converter shown in the figure, like will regulate and the voltage to fill the battery and regulate it to feed the load. The bidirectional converter will help the system produce energy. Produce the to transition between the directly providing energy to the building demand. Like you can see, we have the 4 gate S1, S1 to S4, and we can change the voltage and to make the gate open or close. And this means the current flow can go different direction with the buck or booster mode. After prototyping, the identification of the component is a big challenge for engineers. And for the components, it not only need to satisfy the parameter and energy need for the system, we also consider the reliability and maintainability and productability. So for the first chart is for the hardware thing, and the type of for the components I choose are a little bit expensive but very safe and have enough redundancy to implement the whole work and can cope with any accident. So this is why I choose these components, and you can easily to see the type I choose, and you also can Google it. And this one is software portion. We have the simulation software. It's piecewise. It's very easy to simulate the components. And also we have the language of the interface is English, and also we have the software to code FPGA. FPGA is the controller. It's lab views. All of choice of components are considered by reliability, maintainability, and productability. high quality components, humanized user interfaces, developed software, clean layout, and precise test can ensure these three characteristics for any system. So for the components choice, any component I chose satisfy the high quality and good performance. So and the user interface, the software I mentioned before is good enough, and the clean layout and the test we do the next. Okay, so not by the way, the comprehensive video and the handout of the introduction for new system would provided by engineers. This one is very important, because the user could not be a professional engineer or professional in this field, so they couldn't know how to operate the system. So the high quality video and handbook of the introduction can effectively help them to operate new system. That's very important. Okay, next we have to do a testing. Testing, good testing means the good system. Before the testing of the system, first aid lessons and machine were prepared to engineers due to a high voltage environment. This is very important because the high voltage environment is very dangerous. It would always threat the health of the engineers. Maybe a little bit error could causes the life of the engineers. So the first aid must be prepared in advance. Let's do the integral test plan is essential after identification of the components. And first we have to do the components testing, because components is very important. We cannot ignore the testing of them just because they are expensive. They have the good parameters. They have a good redundancy. So we also need to test them one by one. Like this is the inductor and the capacitor I chose, and maybe we can give them. We have the setup. We have give them a source and in a normal circuit, and we have the digital multimeters. We have the oscillators to know the health of them. So next, after components testing, we have to do the testing of the subsystems. So we have the 5 subsystems. It's a big work. For the control subsystems, we have to do any instructions and to make sure it's work. And for the collected subsystems, we need to test the health of the solar PVs. We can know its work. And also for the protection, no, we have to know the BMS is worked. We have to know the fuse, the cover is good enough. And also we have the picture. This is a battery. This is an example to give you guys in the PowerPoint. And we have to know the every cell for the battery bank is good enough. Maybe a little bit error could cause a big accident. And also we have the power conversion subsystems. We need to know the converter we designed is work perfectly. We have the buck mode or boost mode. We have to test the the current flow goes to the converter can go to bi-direction. So maybe can goes to the battery, also can goes to the building node. And that's the testing of the subsistence. And finally, the success of the testing of subsistence testing, it doesn't mean the system can work perfectly. So when you combine the all of subsistence, you cannot imagine what happened. So finally, we have the testing of the integration, and we have this is the table. This is the result. We do the testing of the integration. We have the 6 steps. The first one is the system should be able to switch from the storing energy to supplying energy, and this one is passed. The second requirement is the battery system's health must be monitored. It's also passed. And the third one is the minimum overall efficiency of system is 80%. The efficiency of the output for converter is higher than 80%, so this one is passed. The fourth one is the battery to load should be at least 85%, and this one also worked by the precise calculation. The system should be determined when the building should use energy from the battery instead of from the grid, and the system can load building automatically. So our system is good enough for smart intelligence. So this one is passed. And the last one is the whole system need to be monitored through the comprehensible user interface. So it's also worked. Everything, every waveform showed in our user interface. Okay, after testing, we have to do the production. The except converter, all of the components come from an external manufacturers. So this too is the example we purchased from the outside. Is the Orion BMS is a famous company for the battery management system, and the inverter. This is the inverter. The Phoenius is also a big company for the produce and design inverter. All components will come from reliable manufacturers in their field. So this is the example. The parameters and the standard are response our requirement through the carefully discussion and communication with the manufacturers. After the production of the components, we have to assembly them. Assembly of the components and subsystems were connected by handwork of the engineers. So because this is a handwork, the wire cleanup is very important. If a mass wire connection would cause an accident and also can influence the future maintenance and repair work. So the cable of the wire cleanup is essential for my design. And also for the assembly and installation, the R&D engineers are changed to the engineers who has enough experience in connection of factory during the process. Because maybe R&D engineers have enough knowledge to development and design a system, but the installation could involve many dangers or technologies like air work and like power connection, etc. the R&D engineers may be not familiar with the technologies and the dangers, maybe cause a big accident. So the installation process, the engineer should be changed. After installation, a perfect service support and the logistics support must provide to clients. Because this is a long duration power systems, maybe you cannot ensure there is no any problem, no any breaks during the long time. So we have the humanized service for the client. In first year, so the service is free. Anything is free. Whatever is the component replacement or repair. And also we also the service also include maintenance in every 2 years for the first 10 years. After 10 years, if you need maintenance, you may be paid, and also you need any service, you need to pay the fee of the components and the manpower. And also for the logistics support, if problem happened, maybe the components and should be changed, the transportation and the vendor of the components are chosen in best methods in advance, which keep high quality and high efficiency. So like if the components broken, the new one will arrive fast, and the engineers who major in repair would arrive fast. Next, the last portion is the cost analysis. The cost report right there. The cost of the entire system is controlled in expected budget, which is $1 million. This table is the cost of the converter, because the converter is designed by engineers, and this thing is the subcomponents we chose for the converter, and the total cost is 1,600 around. And next, this is the other component cost. We have the expensive battery bank and the solar panels, because this is a big power energy. This must spend a lot of money. And also I have the battery management system. It's not cheap. And the controllers, and also we have a lot of sub-components like wire, transducers, tools, and cables like that. So this is not too cheap, because there are a lot of things. And also we have the source simulators. The simulator is expensive too, because we have to simulate big power, big energy. So a normal simulator doesn't work. And we have the inverter is 2000, and the total maybe is $0.8 million around. Next, this is the cost of the manpower. First, we show the number of the engineers. We have 2 system engineers. We have 8 R&D engineers. We have 3 logistics workers, and we have the 8 engineers of the installation. And for different engineers, we have the different hour price, and we have the different worked hours. The total cost have been specified by the table, and the total could be $0.16 million. Okay, all the process of the system design is finished, and many challenges could be met during the process of the system design. The first is trade-off. The trade-off is hard for any system, any project design, because we have the limited schedule, we have a limited budget, and we have the lot of requirement like efficiency, like the payback period. So how to make everything perfectly is a big challenge for us. And another challenge for me is the to learning the knowledges. A lot of related knowledge should be known by a long time, because maybe some knowledge of power you never touch before, you never know before it, you should pay a lot of attention to them. So this one is very hard for me, but the related knowledge can help us to control the processes in design and development. So this is essential, but this is a challenge. Sorry. And next, the safe logistics, testing, and service, and others. Any process would be involve a lot of communication. Sorry, a lot of communication and power on work. Obviously, communication is very difficult but useful for any project. You have to communicate with the engineers or manufacturers. That's a big challenge. Maybe you may have a lot of argument with them. Maybe there are a lot of unhappy experience, but how to make them aware is the art of the communication, but it's big challenge for any people. Another thing is the power. So maybe we have schedule, we have limited time. You have to pay attention to a lot of things for the system design. So you have to spend a lot of power to them. That's also a big challenge. In conclusion, new system is feasible by the evaluation of the testing result and the cost report. So it would save a lot of money and the fossil fuels after several years if no big accident. Through the project and the lecture of the system engineering course, I learned many special characteristics about system engineers. And the three different graphs show the three characteristics I learned. First is caution. Because the system engineer will focus on all of processing. Caution is the first characteristic for implement the process. Also, the system is the power one. Maybe a little bit error could cause a big accident. So caution is an important characteristic I learned. Also, another one is easily to know is discussion. A good discussion can ensure the good system project, because for any process we have to communicate with the engineers or manufacturers how to get the best things we want is a discussion. Maybe one person's idea have a shortage. The more discussion can help us to find the shortage and to solve them. The last one is teamwork. How to make the power together. The teamwork is the only way to to make them come true. So these three characteristics is I learned from the project and the lecture of the system engineering. Another thing I learned is how to improve my learning ability, because as a system engineer, I have to pay attention to all of process. So maybe there is a lot of knowledge I have to learn, but I never touched before. So how to learn fast is the important thing I learned from the course. Making the learning plan and focusing on the highlight of project is the key for this one. Last one is focusing in all processes in system design is the most important thing for system engineers. Don't like R&D R&D engineers. They just focus on the development and the design. They just use their knowledge to the design. It's good enough. But the system engineers, they have to focus on all process and to give the other engineers a right direction to work. The system engineer like leaders, so they must to make the process work successfully. A planned process of system design can easily save a lot of time to make system work perfectly. So that is the presentation for course system engineering. Thanks for your attention.